Welcome everyone to the first afternoon session. Our first speaker is Stuart Wyithe, and he will be telling us early galaxies and the reionization of intergalactic hydrogen.
Thank you. So I recently moved to Mount Stromlo and Siding Springs Observatories as the new director. So the ITC has spawned at least one observatory director. Avi, you'll be pleased to know. I'm not sure if I'm the only one, or if that's a good sign for Australian astronomy. Time will tell.
Are these your members?
And these are some of the colleagues up at Mount Stromlo, sitting outside my office. So like everyone else here, I'm pleased to be back at the ITC. I visited yesterday, Lisa and other colleagues, and couldn't find my way back in. I was here in 2001 and I couldn't remember how to get into the building, but once I was in, I could still find my way to Avi's office, so not everything was forgotten. So I'm going to talk a bit about reionization and the connection to galaxies, and the introduction's been beautifully given for me this morning, both in terms of new discoveries of high redshift galaxies and in terms of what reionization is. But I think there are still questions, many open questions that we would like to solve that keep us studying this topic, and they're almost the same questions as they were 20 years ago, but I think we are making significant progress. But things like, in detail, what are the sources, when was reionization occurring, what was the topology, where did it start, and how was it regulated? And these are things that we had no idea about 20 years ago, some idea about now, but in detail still have a lot to learn. So in terms of constraints, in 30 seconds try to talk about some of these. So cosmic microwave background gives us a constraint on the integral of the amount of ionized hydrogen between us and the edge of our observable universe. The atomic hydrogen gas in between is probed by Lyman alpha scattering, and in different ways, through resonant absorption in highly ionized IgM, through damping wings of very highly neutral regions, both in Lyman limit systems and in neutral IgM itself. And of course, as we've now getting increasingly large amounts of information about the properties of star-forming galaxies, most relevant for reionization, out to redshifts that could only be imagined just a handful of years ago. So when we put these together, we get a picture of a reionization that started to commence in earnest at a redshift 9 or 10 or so, finished between a redshift of 5 or 6, was due to photoionization and likely due predominantly to galaxies. And so that's the paradigm in which I'm going to discuss reionization today. So whilst the CMB gives us an integrated picture of the history, and Lyman alpha probes give us a picture of the ionization state along specific lines of sight and at particular redshifts, a future we should be able to see the intergalactic hydrogen, neutral hydrogen content in 3 dimensions. So make maps of the atomic hydrogen and the neutral hydrogen. And telescopes, as we've already heard, telescopes like MWA, HIRA and LOFAR are already making measurements like this, and in the future SKA will add to that. And the sorts of observations that it would try to make, SKA in particular has a design which should enable imaging of the intergalactic hydrogen, and so this is an attempt to mock up what an idealised observation might look like. In the top, on the bottom, measurement of the power spectrum, so the statistical fluctuations in the atomic hydrogen brightness temperature and how that evolves with redshift. And so these are measurements that we would aim to make. Now, these measurements are occurring on very large scales, many tens of megaparsecs, 100 megaparsecs. Galaxies occurring, galaxy formation and the properties of galaxies occurring on much smaller scales. And so there's a theoretical challenge to try and link these two in order to try and understand what roles galaxies have in reionization, and conversely, what reionization can tell us about formation of galaxies. So there's a range of ways that people have tried to simulate this connection. On the left, I've the two most extreme examples. So we've already heard in a beautiful talk this morning about the progression of large-scale hydrodynamic simulations, and I think this afternoon we'll hear about the coupling of radiative transfer into these to do a fully consistent calculation of reionization. At the beginning, and I include this analytic plot because it was produced here at the ITC, this is an analytic model looking at the relationship between the collapse of structure and the evolution of reionization, to try and understand, as a first question, whether structure formation and reionization are obviously consistent with what we know about how baryons turn into stars and galaxies. So I was amused while Volker was giving his beautiful talk this morning about in the early 2000s with the tens of thousands of lines of code and the many cores that were being recruited in the basement of the ITC, and Avi and I were busy trying to keep our code base under 100 lines and on just the one core on a laptop. So and the difference in sophistication that results. But I wanted to talk about some simulations today that sit in the middle and try to utilise the combinations of aspects of these two techniques which can be powerful in the right circumstances, and this is semi-analytic models. So here I'm going to use a model which is built on an n-body simulation, so identify the collapse structures and their gravitational interaction from a dark matter only simulation, but then combine that with analytic models of how we understand the cooling of baryons, the production of stars, the deposit of energy from those stars, mechanical and radiative, back into the interstellar medium and into the intergalactic medium, and couple that with a semi-numerical style attempt to calculate the effects of radiative transfer on the intergalactic medium. And so I'm not going to talk about the details of the model, but this is an example of the output that you get showing, and the idea here is that you can aim to calculate how the galaxy's forming, what their summary statistics are, what the gross properties of individual galaxies are, and try and correlate that with what you predict happens to the intergalactic medium. So there are two reasons why a model like this can be useful, and semi-analytic models in particular need to be used in the right way. So what I'm showing here is an attempt to try and understand which sets of parameters that describe the analytic properties of the galaxy formation and the obscuration from the dust, what sets of those parameters can describe the summary statistics of the luminosity function and the relationship between continuum slope and luminosity. And so you can do this kind of exploration with a semi-analytic model because whilst the computation is not cheap, it's relatively cheap, so that a simulation can be run in some seconds rather than some hundreds of hours. And so you can make generalized conclusions about properties of galaxies that you can see with simulations like this, and try and understand to what extent, just because your model fits the data, does that mean that that's the right model, or are there degeneracies in the parameters that you're exploring? The other reason why a model like this can be useful in the context of studying reionization is volume. And so the plot on the right here shows a large-scale 21 centimetre fast simulation, kind of ridiculously big simulation, but this was designed to try and cover the whole of the MWA reionizing field, which is shown by the red circle, and to capture all of the statistics in that field. The blue, the smaller circles are Hera, LOFA, and SKA, and I think SKA is one of the smaller ones, and I think Hera is the blue one. But the point here is that that a simulation which is of order 300 megaparsecs on a side is minimally needed in order to look at the statistical properties of a simulation, of an observation like this. And in addition, if you want to capture physics of X-rays and the resulting thermal evolution on the intergalactic medium, you also need simulations of that scale. Okay, so a simulation like this by construction will fit the luminosity functions or the stellar mass functions or whatever other summary statistics you use to calibrate them. And it's then interesting to go and have a look at what they predict for other less observable quantities. So in this case, the relationship between luminosity and halo mass. So a question to ask is, if you believe that galaxies are forming within dark matter halos, what is the mass of the dark matter halos at the stellar masses that you're observing in the reionization era? And you can probe that by looking at galaxy clustering. So there's an example of that here, measurements from redshifts 5 to 6, and the evolution with luminosity and the evolution with stellar mass is the different panels. And we see that models like this do a good job of describing that clustering, and on the left is the predicted relationship between virial mass of the halo and the brightness. So at -18, we're looking at galaxies of inside 10 to the 10 solar mass halos, and that's, I think, becoming the understanding of what the halo mass scales are that we're looking at in these high redshift galaxies. A more interesting, maybe, example of this was a great observation that was made by Pascal Huche and his student Leonova. So here we looked at the model and the question from Pascal was, what are these very bright galaxy Lyman alpha emitters that were discovered in the Goods field with those phone numbers? Are they likely to have galaxies surrounding them? And the prediction from the model was we should expect an overdensity. If you look a couple of magnitudes fainter in the UV, should be an overdensity of 3 to 5 up to 10 was the prediction. And indeed, that's what's observed when Pascal went back to look at these galaxies with deeper HST observations. So when you look at these high redshift sources, you see this overdensity, which is associated with clustering and is helping, presumably, to drive large-scale H2 regions around those objects. So when more recently, if with a model like this, the interesting thing to ask is well, my model's calibrated on galaxies at redshifts 4 to 6 to or 7. We're now being presented with galaxies at much higher redshifts, many galaxies at redshift 12 to 13, some suggested galaxies at redshift 16. What does the model say about galaxies like these? Are they in the simulation? If they're in the simulation, what sort of properties do they have? And so what's plotted here is 3 examples of spectroscopically confirmed galaxies at redshift 12 and 13. And I just wanted to talk about galaxies like this in the simulation. So the first thing to note is sort of number density. So remarkably now, luminosity functions are being presented to us out to redshift 12. I find this remarkable. And this galaxy formation model, which is very standard model, is producing galaxies at the faint end at the right density, at the bright end close to the right density. And the thin lines on the upper left I'll come to in a minute. And so that's fine. So then it's also interesting to ask, well, if these galaxies in particular, if I look at the spectral energy distributions of those galaxies, do I find them in the simulation? So for a given star formation history, we can use stellar synthesis models to calculate what the spectrum should look like, calculate the flux in the same bands in the usual way. And so that's what's plotted in these 2 cases. And so you see that we can identify analog galaxies in the simulation which have the right spectral energy distributions and the right spatial densities to describe what we're seeing in this redshift 12 or so population. And so that's, I found that a bit surprising and interesting. And so then you can ask, well, if I've got a population of model galaxies, what can I learn about the physical properties, both the sorts of physical properties that you can learn about by looking at the SED with spectrals without a full model, and also properties like dark matter halo mass, region, size of H2 region that they produce, etc., that you can't get directly from observation. So an example of that is shown here, and I've broken the rule where you don't put a plot that you can't read every axis on. But what I'm trying to show here is that if you look within the population of galaxies produced by the simulation and look for the likelihood that a galaxy describes the spectral energy distribution of the observed galaxy. So in this case, it's this GZ13. So you can then calculate the space in which the parameters that describe things like escape fraction, things that describe the luminosity of the galaxy, the specific star formation rate, the stellar mass in the galaxy, parameters describing the obscuration, etc. And you can also calculate properties like the fraction of cold gas in the galaxy, the virial mass of the dark matter halo, and the size of the H2 region that it's producing during reionization. So in models where you can observe the quantity or try and measure it directly from the spectrum, we're finding that this population of galaxies produces properties which are statistically similar, but we can also do things like measure the halo mass, and again, we're getting values like 10 to the 10. So this kind of, I think this kind of analysis is interesting for trying to put these galaxies in context of all of the whole population of galaxies that are in our models and potentially in the real universe. The other point I wanted to make here is about what does a model like this standard galaxy formation model say about potential redshift 16 galaxy candidates. And here the story is very different. The model has no such galaxies in it. And the other lines plotted on here, there's the thin lines just to the left. Use my pointer. So these two lines are lines where, so we have an n-body simulation. We can allow all the gas in the simulation to cool and to form with maximal star formation. Okay, and if we do that, then we get a density that looks like this. The thick grey line is a similar analysis that was done analytically by Charlotte Mason a couple of years ago. And you see that if you wanted to produce this kind of density of galaxy at that redshift, you need extremely high, extremely efficient star formation and formation mechanisms that are different from what we see in galaxies. And this is a point that was already made this morning as well. So just to have a quick look at the SED for this galaxy. So this is the SED of the brightest galaxy in our model under our normal galaxy formation scenario. It's very much fainter than the SED of this galaxy candidate. If I want to produce an SED consistent with that, I need to have maximally efficient star formation. But the model does have quenched galaxies at redshift less than 6, which have spectral energy distributions which are similar to this, or also highly obscured in very dusty galaxies. And so spectra are needed, of course, for these high redshift galaxies if they are to be real. If they are real, that tells us something really interesting about our galaxy formation models because they are indeed broken. Okay, in my last 5 minutes?
Yes.
Okay, I'm going to talk a bit about, go back to 21 centimetre power spectra. So I mentioned at the start that the point of doing this work was to try and link what we know about galaxies to what we know and might know in the future about 21 centimetre fluctuations. And so the point here, one point to make here is that that whenever all models of the reionization process, they differ in detail depending on how they've been computed, but they are all producing an inhomogeneous reionization with quite relatively sharp edges on the edge of the H2 regions, and this is because if we think reionization is dominated by UV radiation. So this introduces features into the intergalactic medium which are not gravitationally driven and which are clustered in a way which reflects the clustering of the sources that drove them. And so for this reason, the shape and evolution of this power spectrum tells you something about the galaxies and the formation of the galaxies, and therefore, if measured in enough detail, the properties that drove galaxy formation. So this is an example of some reionization predictions, 21 centimetre predictions from this fiducial model that I've been showing. So it shows the reionization history, the luminosity function, a map of the ionization, and then depending on what's assumed for the unknown contribution of X-rays from the high redshift galaxies, different light cones. So in particular, a galaxy population with a very low efficiency of X-rays at high redshift gives a cold intergalactic medium relative to one where the intergalactic medium is, cold and therefore highly absorbed 21 centimetre signal compared to an intergalactic medium that's been heated. And so what's plotted here is, on the bottom right, is the power as a function of redshift for these different models. And you can see, as Anastasia already showed this morning, the great difference that you get depending on what's happening with X-rays. So we can, as Anastasia talked about constraints at cosmic dawn, we can also start to look at constraints in the reionization era. And so what I'm showing here is some from the Murchison wide field array at a particular wave number, constraints as a function of redshift of the power. And this is a paper due to Brad Grieg, where he plotted on this in a phase space for 21 centimetre fast models, which is 21 centimetre fast is a phenomenological model that describes galaxy formation with parameters like star formation efficiency, escape fraction, minimum halo mass, and this fraction of energy in X-rays. And these are all models which are excluded by the results here. And this corner plot shows the probability of exclusion. So there are a series of models which have low escape fractions, so reionization occurs late, and very cold, a low X-ray contribution, so the IGM is cold, and this is a region of parameter space where models are already being excluded. So the question is whether any of those models are consistent with what else we know about reionization. And so in that corner plot, these three models here would sit in this position, and with this one being marginally excluded. And so if I go through the process of putting that model on this plot, we see that these models, which are otherwise consistent with everything we know about constraints on reionization, are already being excluded by, a model with very low X-ray contributions at high redshift is already being excluded by these observations. Hera, more recently, has provided even deeper constraints, but at a bit higher redshift and at higher spatial frequency. And similarly, these constraints are ruling out these very low X-ray models. So this is very exciting. We're already starting to see, even though we haven't detected reionization in 21 centimetre with these interferometers, we are starting to rule out regions of parameter space which are otherwise allowed by our observations. So the last thing I want to say is to look a bit forward into the future. So I can, again, take this same fiducial model and predict its power spectrum and the error bars that are going to be available, or the constraints that are going to be available on this from the square kilometre array. So once we have a detection rather than limits, then we can start to ask questions about measurements of parameters that describe the galaxy formation. And so that's what's shown here, is a forecast using a Fisher analysis of constraints on quantities that describe galaxy formation in this semi-analytic model. So these are quantities like, so quantities which describe the SED in the X-ray regime, but also quantities that describe the star formation efficiency, how that star formation efficiency depends on halo mass, how the supernova feedback is, how strong that is, how efficient it is, how it depends on halo mass and so on. And in principle, those parameters can be measured at the 10% level just using the SKA observations. So you can do that kind of analysis with the luminosity functions, but only in those peak of the iceberg still galaxies that can be observed, whereas your 21 centimetre analysis can see all galaxies. And so in combination, we'll get the SKA observations and the Hera observations of the power spectrum will provide us with detailed information about galaxy properties beyond what we can get just by observing them directly. So I'll finish there. With the summary, galaxies at redshift 12 seem to have properties described by a generic galaxy formation model, but very high redshift potential galaxies do not. The astrophysics of reionization is starting to be constrained by telescopes like MWA and Hera, but those telescopes in their full SKA and Hera in the future will be able to measure detailed properties of the galaxy population. Thanks.
Question?
Hello.
Observatory Director. Glad to see you back. So I did not hear you say too much about AGN.
Yeah.
Don't they do much on reionization? Have you put any constraints on that?
So we haven't explored yet the red dots. We have put AGN in the simulations to study quenched galaxies at redshift 4 and so on. And in those models, AGN make a small contribution to reionization. I think there was in the past when there've been claims of faint AGN from stacked X-ray, and it looked like there was a significant contribution to flux from faint AGN. When we modelled that, we found that that most of the UV flux in those stacks was due to the galaxies hosting the faint AGN. So I know this is a topic that remains open, but in no calculation I ever did showed AGN to have a significant contribution.
I was thinking because now people are saying that high redshift black holes are overmassive, right, for the stellar content of their first galaxies. So maybe those AGN, assuming they are accreting a lot, might be a lot more important than people think.
Yeah, it could be. So I think they're still rare, but I think that those calculations all need to be revisited in the context of the new recent observations. But they'll have to make a difference, an order of magnitude at least, relative to previous discussion.
So I think we're all going to ask about our favorite objects. So Ramesh asked about AGN, I'm going to ask about supernovae. And, is there something in terms of both the feedback and the assumption about the supernova rate and the types of supernovae and how much luminosity they add that could influence these results?
So how much luminosity they would add in terms of...
I was wondering if some of this, high luminosities could be due to the effect of contribution from supernovae.
So to answer the first part of your question, so the IMFs are standard in these models, low metallicity, but not POP3 or anything. So they're not top heavy. So the number of supernovae and the yields, etc., are calculated from standard population synthesis. So the effect that they have is on the feedback, so reheating the gas and potentially ejecting it from at least from the disk into the CGM, but potentially into the IGM. So that is done with in a framework which is standard, and I think it's with the same physics as within a hydro, but implemented analytically. So, but the efficiency with which that happens is calibrated by the observations. In terms of production of luminosity, I don't think there's a significant contribution. That has been calculated, I think. Unless it's POP3, right. But in these POP2 galaxies, the radiation coming out of the supernovae is in a time-integrated fashion less than the radiation coming from the star, from the young stars, I believe. I mean, that has been, I haven't done that, but that has been calculated.
Other questions? Okay, so if not, let's thank Stuart again.